Alright, so when we then left off, we had started looking at this concept called an electron configuration. And I wanted to expand on this a little bit more because there is a certain order that we're going to follow when it comes to filling these orbitals in. And it had to do with that energy diagram that we made in our previous video. So as a quick summary real fast, we talked about how when we're looking at orbital diagrams of multi-electron atoms, that there's kind of a filling order, right? We go from a 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and you're kind of probably noticing a pattern here in our electron configuration. And as we talked about, because of the Coulombic attractions, we always fill from the bottom up. Hund's rule tells us that all degenerate orbitals are filled one at a time, and the Pauli exclusion principle says we have to have one electron up and one electron down to give each electron a unique set of quantum numbers. And so we're going to continue along this same trend with just a few more examples before we take a look at how this piece sets up. So in this case, when we take a look at our orbital diagrams, let's take a look at a couple more examples. We're going to take a look at the electron configuration for silicon. So when we take a look at silicon, we're going to kind of go in order here. We have our 1s orbital, our 2s, our 2p, 3s, and 3p orbitals are going to be the important ones we need for silicon. And we have 3 each of our p orbitals. So all I did is I drew my energy scale running left to right instead of up and down in this diagram. So it looks a lot like the orbital diagram, just kind of tilted sideways. This is going to help us out fill this in. When I take a look at the electron configuration, or at the atomic number for silicon, we have an atomic number of 14. So this means I'm going to have 14 protons in the nucleus. I'm going to have 14 electrons to fill up in the electron cloud. And so I'm going to fill this up according to the Coulombic attraction rules. So I have to go energy level, and then one up, one down. Same thing, one up, one down. My 2p's, 5, 6, 7 electrons. 8, 9, 10, 11, 12, 13, 14. So what I'm able to do then is take a look at my electron configuration, and now I can write this out according to what we've drawn in. I have a 1s2, 2s2, 2p6, 3s2, 3p2 as an electron configuration. Now, when we take a look at kind of how this is set up, we're going to see that everything in the 1 and 2 energy levels are full, but we're going to have our s orbitals, our third energy level electrons are still going to be empty, or not empty, but not quite filled up all the way. So in this case, whenever there's a filled shell, we call this part of the core electron system. So anytime we have these filled shells, it's the core electron system. Anytime we have an electron, and then the electrons that are left over, not in the completely filled shells, we're going to call these valence electrons. And a valence electron is an electron in the outermost energy level and we'll see that these valence electrons are also responsible for chemical reactivity. So in this case, I would say that silicon has 2 4-valence electrons in the atom. Same thing, when I take a look at carbon, carbon has an atomic number of 6, I'll see that it follows a similar pattern. Here's my 1s, my 2s, and the 2p. But carbon only has 6 protons and 6 electrons, so I fill them in accordingly. And when I take a look at the electron configuration for carbon, 1s2, 2s2, 2p2, my 1s2s are the core electrons, and my 2s2, 2p2 are our valence electrons, because now the second level is the outermost level. So in this case, I have a total of 4 valence electrons. So you'll notice that carbon and silicon, in the periodic table that we talked about in our last discussion, have really similar chemical reactivity properties. When we take a look at their electron configurations, they both have the same number of valence electrons. And it turns out that the periodic table is set up in such a way to help make this electron configuration very straightforward. So when we take a look at kind of how this connects to the periodic table, then we'll see that the periodic table is divvied up into 1, 2, 3, 4, 5. 1, 2, 5. Here. All right, I'm actually going to bring this down one more. There we go. All right, so we're going to take a look at, when we take a look at the periodic table then, we'll see that each part of the periodic table represents a different set of electrons. And we can use these different regions to predict what they're going to be. So in this case, any element in these first 2 columns right here are going to have valence electrons in the s orbital. Or we'll see their electron configuration ends in s. So we call this the s block of the periodic table. Anything over on the right, this section over here, we call the p block, because we'll see their electron configurations end with p electrons. And we continue the same trend. Anything in this general region of the periodic table is called the d block, because the electron configuration ends in a d. And alas, anything at the bottom, this region down here, is called the f block. And so when we take a look at these electron configurations, we'll notice that across the board, anything in this first column ends in an S1. Anything in this second column ends in S2. As we're going through with our main block again, we'll see that that's a P1, P2, 3, 4, 5, 6. And so when we take a look at some of these, if I were to take a look at, say, chlorine, for example, chlorine has 17 total electrons, we'll notice that chlorines would be right here on the periodic table. So it'll end in a P5. The other thing you'll notice is that when we took a look at carbon, it's in the second row of the periodic table, and so it ended in an energy level of 2. Chlorine's in the third row, so its final electron configuration is going to have a 3p5 at the end. So we can kind of use the periodic table, or we can say the periodic table was influenced by the electron configuration of our elements. Now, one thing that's going to make this kind of easy, I'm going to fill in some of these noble gases right here. Anytime we take a look at the configuration for something like helium, that's a 1s2. For neon, it's a 1s2, 2s2, 2p6. Again, it has those completely filled valence levels. Etc. So anytime we can replace a portion of this, we can kind of shorten up our electron configuration a little bit by substituting in the core electrons for a noble gas. So in this case, I could also write the electron configuration for chlorine as neon, because it's the core with the valence of 3s2, 3p5. And so when we take a look at the main group elements, our S block and P block, our rules are very straightforward when it comes to determining our electron configurations. So, this gets a little different though when we take a look at the transition and intertransition metals. So for example, anything in the D block or the F block. So when we take a look at these D block and F block elements, you're going to see that you follow the same general principle. However, there's going to be one difference. And that one significant difference that we're going to be coming across is going to be how we fill in those elements. So what I'm going to do is draw this in for you. So let's take a look at these D block and F block elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have a little bit more space to write. All right, so I'm allowing 2 spaces for each element that we're going to be looking at. So when we take a look at how these are set up, and I write, if we start with like scandium and titanium, vanadium, all the way across, we'll see that our electron configuration starts off with the same idea. This is period 4, row 5 of the periodic table. You can see rows are the same thing as period. And so when we take a look at this, when we filled up our stuff, we went 4s2, 3d1 when we took a look at our electron configurations. And as we go across 4s2, 3d2, as we keep going, this becomes 4s2, 3d3. But when we get to chromium, we're going to see that we now have the option, we're now actually going to switch this around. So this will be 4s1, 3d5, 4s2, 3d5. So when we take a look at these, I'm going to blow this up a little bit for you. There we go. Should make this a little bit easier to do. Let's fill these in so they're better to read. So when we take a look at scandium again, we have a 4s2, 3d1 configuration. So we have 4s2, 3d2, 4s2, 3d3. But when we get to chromium, this is when it switches. It becomes 4s1, 3d5. And we'll see that the same trend, 3d5, this becomes 4s2, 3d6, 4s2, 3d7, 4s2, 3d8, and then when we get to copper, we see that same switch that we saw in chromium. This becomes a 4s1, 3d10, and then zinc becomes a 4s2, 3d10. And we'll see that that same pattern repeats for yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. Down here in the fifth period elements, we'll see that they take the same approach, where it's that 5s2, 4d1 as we go through our structure, and it repeats the same patterns. And we'll see that same switch when we get to molybdenum. It becomes a 5s1, 3d5. That should be a... Made a mistake. That's a 4d... Man, I cannot write this in today. It actually makes it a little cleaner to read. So in this case, it's a 4d5. There we go. 5s2, 4d5, 4d6, 4d7, 4d8, and then we'll see that we jump that same switch again to give our 4d10s and a 5s2, 4d10. And so the question is, why does this happen? Why is it that around molybdenum and technetium, or around these general two areas in the periodic table, that we observe this switch? So if you'll recall, all of this is determined by atomic spectroscopy, and so they're able to determine the wavelengths of light and all those other good pieces. But one thing to remember is that as we get higher up, especially if we're looking at the 4s energy level versus the 3d energy level, these are very close together. And so what ends up happening is that once we fill up an orbital with electrons, the energy actually drops down a little bit. Same thing when an orbital is half filled. And this is because of kind of the ability of two electrons to sink a little bit closer to the nucleus, which gives them a lower energy state. So it's just an observed phenomenon that occurs. So in this case, the reason that this happens is when we're able to fill up the d orbitals halfway, they'll actually drop in energy below the 4s line. And so now the 4s becomes the last orbital filled. So you remember, if you can have a d5 configuration or a d10 configuration, you're going to see that you take the s electrons first. or that the s electrons get filled in last. All right. So this kind of wraps up then how our elements are filled in with their electron configurations, and how we can use the periodic table to predict all of this. In our next video, we're going to start taking a look at why different elements inside the periodic table have different reactive properties.